Yes, we'll move it. Yeah, we'll move it. Yeah, we'll move it. Yeah. You want a time?
I can also just look at that.
Thomas, I just unmuted the podium mic.
Okay.
And also, I can see that we're live streaming, so I think we're ready to roll.
Just 1 minute.
It's okay. It's all good. It gets edited out in post. Right, Max? I don't know if you can hear me. Okay, so we have Sangeeta's now. It gets edited. So if an emergency happens, you've got the right ones.
No.
Right. That's the only fear, is that you really won't download them.
Yeah, I want to access this house because actually I want to.
Kevin, does this look good? Okay.
I will give a intro. I'll give a couple minutes actually. So this should work, I guess. Okay, now it works. Perfect. All right, I will get us started. Thanks everyone in person who joined us. I'm Hannah Braun. I'm the Senior Media Relations Specialist at the Space Telescope Science Institute. And thank you everyone else who joined us online. Welcome to our Writers Workshop at the Inspired by Emerging JWST Results Conference for Roman. As many of you know, Space Telescope Science Institute serves as the Science Operations Center for Roman. This, of course, includes lots of things. We're engaging the science community in the definition of Roman's core community surveys. We are also working with our colleagues at the Roman Science Support Center at Caltech IPAC, commission and operate the ground systems necessary to deliver science-ready data products and platforms for the scientific community. Also, just like with Hubble and Webb, we play a big role in communicating Roman science to the public and the media. So with this workshop, we hope to begin to prepare journalists, other outreach professionals for the science themes, discoveries, and concepts that we expect to come up when Roman launches and performs science. So we'll first hear from Dr. Ami Choi of the Goddard Space Flight Center, who will give us an introduction into the mission. Then Jessie Christiansen of Caltech IPAC will discuss Roman science in our local universe. Next, we'll hear from Dr. Sangeeta Malhotra of NASA headquarters, who will give us insights into Roman's extragalactic surveys. Then Dr. Benjamin Rose of Duke University will take us through Roman's studies of the dark universe. And then Dr. Suvi Gezari will finish up with the dynamic universe and Roman. So we've left some time after all the presentations are done for questions. So for everyone that's virtual, just drop any of your questions in the Blue Jeans chat and we will get to them. And then we'll also take questions from the room at the same time. So I will leave this to Ami.
All right, well, thank you very much, Hannah, and also thanks to the organizers for putting together the workshop and also the conference overall. And thanks for everybody in the audience and those who are with us online. So I have the honor of kicking us off today to start with talking about the Nancy Grace Roman telescope, also how it relates to JWST and the science that Roman's going to do. So for an overview of the Roman Space Telescope, so this was the top-ranked large space mission selected in the 2010 Decadal Survey, which, as a reminder, is a place where scientists who are involved in astro-related topics of research get together and prioritize their the main science focus for the next 10 years. And so this is very much like Hubble in terms of the power and resolution, but 100 times the field of view. And then, yeah, the main topics which we'll come back to is that we're going to study dark energy, planets outside of our solar system, and general astrophysics and investigations. So on this diagram here, we can see some major components of the observatory, which I'd like to highlight. So there's, for example, the solar array and sun shield at the top here. So that's involved in shielding the telescope from the sun, but also powering the observatory. We also have the outer barrel assembly here. So this is a structure which is responsible for having some of these other components like the solar array and sun shield, but also making sure that the mirrors stay cool and keeping stray light out of the telescope. And then there's the spacecraft at the bottom here. And there's six, the reason why it says 6 times here is that it has 6 compartments. It's 6-sided. I mean, each of these compartments contains electronics that are really important for running the rest of the telescope. And then also the communications is done through this high gain antenna up at the top right. Now, the 2 instruments that will be on Roman are down here. So the coronagraph is actually on the other side. This is a technology demonstration instrument. A lot of the science that I'll be talking today will be conducted with our science instrument, the wide field instrument. So people often ask the question, what sets Roman apart from the James Webb Space Telescope? Why do we need another large space telescope? And really, these 2 telescopes are very complementary, and they don't try to look at or approach science in the same way. It's quite different, actually. So we can see that by comparing the overall setup of, what the size of the mirror is and what the detectors look like. And so on the left side here, and on the top we see for JWST, the primary mirror is very large. It's 6.5 meters across. And overall, it collects more than 6 times the light of what Hubble and Roman can collect. And so Roman is here on the bottom, so it's the same size as Hubble, 2.4 meters. Now, another big difference is when you look at the detectors on the focal plane. So here you can see that NIRCam, which is the imager for JWST, is composed of, for one set of wavelengths, 8 2000 by 2000 pixel sensors. And then for a longer set of wavelengths, another set of 2K by 2K sensors. But overall, and this part of the image here shows what that subtends on the sky. And if you compare those detectors to the 18 detectors in Roman's focal plane, you can see that the actual region of the sky that's covered is much, much larger with Roman, so a factor of 100 times larger. And so the important thing to take away from this is that Roman is really meant to survey vast areas of the sky very efficiently. So we can see this again if we look at this image where the original Hubble picture of the pillars of creation is there in the center. And then this is a simulated image of what the Roman field of view would look like. But the data, of course, is taken from the ground since Roman isn't flying yet. And then we can update the Hubble image with the JWST image, which gives us even greater detail in the pillars of creation. But we can see that in a single snapshot, Roman can still capture that area much more efficiently. So the overall area being the Eagle Nebula. So this is another illustration of the efficiency of Roman in capturing vast areas of the sky. And so this is the Andromeda Galaxy, and then it takes over 400 pointings of the Hubble Wide Field Camera 3 to cover that area. Whereas for Roman, it takes 2 pointings. And this isn't even really including the fact that it takes the observatory less time to change where it's looking at the sky. All right, so on that note, the power of Roman is really not just about its huge size, like field of view, or the size of the sky that it covers. There are really other aspects of the observatory which make it very powerful, including this fast slew and settle time. And then there's another aspect here where, so we love Earth, it's really great, but for observing distant, faint things, it's not so great because there are things like Earth shadows that we have to avoid. There's also Earth's magnetic field causes certain regions of increased ionizing radiation. We have to avoid that too. So we have decided to put the Roman Space Telescope at L2 along with JWST, and that will help give it other aspects such as a well understood and stable point spread function. And then it'll have a very stable thermal environment there. Another aspect is that the structure of the telescope is rigid to help shield it from or rather isolate it from the vibrations of the spacecraft. And it also is very stable in terms of how it can point. And the last thing I'll mention here is that Roman has excellent flux calibration owing to an internal subsystem, calibration subcomponent, which is called the relative calibration system. And this is really important for calibrating the flux over many orders of magnitude in signal. And for more details, you can look at this white paper by Akeson et al., 2019. All right, so this is actually kind of an outline for the rest of the talk, where these are the main mission objectives of Roman. So the first one here, and I'll go through each of these in a little bit more detail, and then the rest of the talks that follow will go into even more detail. But the main objectives include understanding the ingredients of the universe, how it evolved, like the history of it, and what is the future. Also looking at the demographics of planets around stars, so planets outside of our own solar system. And one thing to note is that Roman is looking at a different range of, for example, orbits of exoplanets around their host stars compared to what previous missions, NASA missions such as Kepler and TESS looked at. And then in general, we will be doing a number of wide field infrared surveys of the universe. So that includes some of the surveys that will be conducted for these, which I'll talk a little bit more about. I'll refer to them as the 3 core community surveys. But there's also 25% of Roman's observations will be spent on general astrophysics investigations. And so that's a really, a lot of time to look at many different aspects of astrophysics, which Sangeeta will talk about later. And then this last item here on technology development. So we also have the coronagraph, which is our technology demonstration instrument, which will really pave the way for future observatories to directly image planets. All right, so this is the picture of the universe as we know it based on observations so far. So we think that it's composed mostly of dark components, so a mysterious dark matter, which doesn't emit light or interact electromagnetically, but it does have an attractive gravitational force, which is how we can detect that it's there. And then also dark energy is a placeholder name for something that drives the accelerated expansion of the universe. And so it has a very different impact on the universe than dark matter or normal matter because it causes everything to move away from everything else. All right, so the first of our core community surveys, the high latitude wide area survey. So this is looking away from the plane of our galaxy out into space. Is looking specifically for the large-scale structure and trying to understand how structure grows over time. So this is a simulation, but showing you going from high redshift on the left down to present day, that there's some sort of webby filamentary structure forming with some very dense peaks and then also voids in between. And so dark energy and dark matter really shape this distribution of matter. And then this diagram on the right is showing an example tiling pattern of the Roman detectors across the sky. And then the idea here is that we want to measure shapes for over 100 million galaxies, and we also want to measure precise distances for over 10 million galaxies. We also have another survey that is also pointed away from the plane of the galaxy, the high latitude time domain survey, but as you can tell from the name, this actually has a particular time component where we repeat the observations, which will be smaller than the wide area survey, so more like 20 square degrees, and coming back to that same field every 5 days. And the idea is to explore the time domain in which there are thousands of supernovae and many more interesting objects, and so I'll refer you to Suvi's talk later. And a subset of these are type 1a supernovae, which are specific standard candles, or so we call them, that can be used to measure precise distances that are helpful for understanding the expansion history of the universe. All right, so there's also this animation here showing one of the progenitors for type 1a supernovae, where we have gas being accreted onto a white dwarf. And at some point, we reach a critical mass where there's a thermonuclear explosion, but we think we understand the physics of that well enough that we can use this as a specific calibration device for cosmology. All right, so together for the high latitude surveys, we have galaxy shapes, galaxy positions, and supernovae telling us together about how structure grows over time and also the expansion history of the universe. And together, this is helping us build a large picture of the physics of the universe, telling us about dark energy, dark matter, and modified gravity. So in the case that perhaps we see any deviation from the theory of gravity that we know and love, we could potentially be able to see this with Roman. And I'll refer you to Ben's talk for more details on this. Now, the surveys that I talked about before, we're looking out of the plane of our galaxy, but there's all kinds of interesting things happening as we look into the center of our own Milky Way galaxy. And so we also have a third core community survey called the Galactic Bulge Time Domain Survey, which again is similar to the supernova survey in the sense that it will monitor 2 square degrees every 15 minutes or so. And then the idea is to look at how the brightness of, say, 100 million stars changes as a function of time. And then we'll use that to discover thousands of planets using the microlensing technique, which I think Jessie will talk about later, and also tens of thousands to potentially over 100,000 exoplanets using the transits technique. And this plot here shows you the region of parameter space in terms of the orbit distance and the planet mass that Roman will be sensitive to. So you can see that this is really opening up a whole new area of this compared to, say, what Kepler did before. And then this is also a picture of sort of how the tiling might go on the time domain survey. All right, so the last thing I want to touch on is to mention that we also have the coronagraph instrument, which can enable the direct imaging of planets in reflection. And so the coronagraph, and you can see this very complicated looking diagram here, and I'm not going to go into the details of how it works, but you can see that it has a very intricate setup of mirrors and such that will help block out the glare of the host star and try to look for those really faint planets that are orbiting that host star. And the contrast could be anywhere from, well, it's probably a wider range than what I put there, but it could be from 1 million for sort of exo-Jupiters to over 10 billion times in terms of the contrast. And so it's a really, really very complex technique. And the idea is that we aren't required to make it produce science for Roman's mission, but this will pave the way for future missions to image and characterize rocky planets in the habitable zones of nearby stars. All right, so there's a lot of things that I didn't have time to talk about. We have many, many different types of astrophysical investigations that are possible. So some of these will be talked about in future talks. For example, Sangeeta will talk about extragalactic science. I think Jessie will talk about some of the nearby, more local neighborhood science. And I think Suvi will talk about gravitational waves. And of course, yeah, Ben will talk about the dark universe again. But there's really a lot here. And one thing that I forgot to mention before is that when Roman's data is taken, it will immediately be released to everybody. So these are surveys that are community surveys, not just for the science community, but really for everybody. The data will be publicly accessible to all. All right, so I'll end by saying we're on track to launch by May of 2027, and we're excited to be up at L2 together with JWST. Thank you.
So Dr. Jessie Christiansen, I will pass it off to you.
Hi, can you hear me okay?
Yes.
Fantastic. And I'm going to go full screen, so hopefully you guys can see that. Hi, everybody. I'm Dr. Jessie Christiansen. I'm the lead scientist at the NASA Exoplanet Archive at Caltech IPAC. You can see my contact details here if you want to get in touch with me about anything. I've put my Twitter handle, maybe a little sadly at this point, but still use it. But yes, feel free to get in touch if you have any questions about anything that's come out of this session. So I'm going to change the title slightly. So I got asked to talk about the local universe. And I'm going to talk about mostly exoplanets and some of the other things that are local. Obviously, it's my expertise and it's the thing that I'm most excited about Roman for. So I'm going to dedicate the majority of my time to talking about exoplanets, but I will touch on some of the other things that are in the local universe that people are excited by with Roman. Okay, so on the topic of exoplanets, you might be thinking, after Kepler, after TESS, now JWST, what are the big questions we're trying to answer with exoplanets at the moment? So here are 3 of the big ones. And you can see that actually a theme of them has to do with life in the universe. So the first one is the search for Earth 2.0. We have not found with Kepler or TESS or JWST a planet truly like the Earth, by which I mean a rocky planet in the habitable zone of a star like the Sun. So the habitable zone being the temperature range where you can have liquid water on the surface if you have an atmosphere like the Earth's. We haven't found one of those yet, so that's a big goal of the exoplanet field. Where is the nearest temperate, potentially habitable rocky planet? Another question, which kind of comes off the back of that one, is about habitability throughout the galaxy. So we're looking for Earth 2.0 because we know Earth 1.0 is inhabited. We know it's habitable because we're here. But one of the things that people ask a lot, and it's a fair question, is why are we restricting ourselves to Earth 2.0? What other types of planets or types of places might be habitable? So one of the questions we're working on at the moment is what kinds of planets might be habitable? And one of the really exciting prospects here, which you might have heard of, is that we have found a lot of rocky planets in the habitable zones of M stars, M dwarfs, small, cool red stars that actually comprise most of the stars in the Milky Way galaxy are M dwarfs. It turns out they seem like they're really good at making rocky planets in their habitable zones. So if those planets are habitable, the habitable real estate in the galaxy increases exponentially. But we don't know yet, and that's one of the things we're doing with, for instance, JWST, looking at the atmospheres of the TRAPPIST planets, which are rocky planets in the habitable zones of the star TRAPPIST-1, to see if they have, for instance, atmospheres. That's like step 0 in whether something can be habitable. Does it have an atmosphere? This is one of the big questions. And then another question that kind of, again, builds off those two is, how common is our solar system? So our solar system has a very specific architecture that many planet formation theories have been geared to reproduce over the years. We have the 4 rocky inner planets, Mercury, Venus, Earth, and Mars, and we have the 4 outer giants. Now, exactly how much that configuration led to the emergence of life on Earth is open for debate. We don't know. Like the role of Jupiter, for instance, how important was it that we have a Jupiter that's shepherding water and comets and material from the outer solar system to the inner solar system, right? A lot of the water on Earth came from comets that were delivered by Jupiter. But Jupiter also has a habit of smashing stuff into us, which has, led to mass extinction events in the past. So, net helpful or net hurtful, open for debate. But we don't know yet if the configuration of our solar system, those inner rocky planets and the outer giant planets, is common or typical, or what is common and typical. And that's partly to do with what we've been able to look at so far. Okay, so let's move on to how Roman will help us address some of these questions. Okay, so as Amy mentioned, there is a coronagraph. There is a technology demonstration instrument called a coronagraph on board Roman. So a coronagraph is a very, very clever, exquisite instrument which is designed to exactly cancel out the light from the star that you're looking at so that you can look around the star for planets. So the canonical analogy that people use is that, trying to directly image a planet beside a star is like trying to directly image a firefly next to a floodlight, right? Like just the contrast is so different. But if you could turn off the floodlight, then you might be able to see the firefly. And that's what the coronagraph is for. The coronagraph on Roman is a technology demonstration instrument. So it is trying to help us push from where we are now, which is being able to image widely separated giant planets. So this image up here in the top right is HR 8799, which is one of the first directly imaged planetary systems we know. It has at least four giant planets orbiting it. This is a movie we've been able to make of ground-based coronagraph data. We want to be able to move from that to something like imaging a planet like Earth around a sun-like star. So Roman won't be able to do that second one, but it's helping us on the way. So there are different types of technology that Roman is trying for the first time that we'll be able to test in flight and see how well we do. And one of the things we want to do is to go from these giant warm planets to giant cool planets. So these HR 8799 planets, they're actually very hot. Even though they're quite far from their star, you can see the scale bar here is 20 AU. So this is astronomical units. Remember that the Earth is 1 AU away, and that Uranus is 20 AU away in our solar system. So, you know, just for scale, these are very large planets very far away. But actually, the system is young and self-luminous, so these planets are still radiating out a lot of heat. So these are actually pretty bright for giant planets. You can actually see them from the ground with the instruments that we have. What we want to do is move to finding cool planets, like the giant planets of our solar system, you know, much fainter. So we want to be able to improve the contrast between the star and the planet. So this is going to be really exciting in terms of characterizing a type of planet that we're not able to characterize at the moment, these widely separated cool planets. Importantly, we'll be able to observe their atmospheres. With this direct imaging, you can take the light and spread it out and look at the light as a function of wavelength and see what's happening in their atmospheres. That's pretty exciting because one of the things we would like to do is to be able to model how different planets' atmospheres look so that when we see other planets around the stars, we can have a guess at what their atmospheres might be like, how hot they are, how much they circulate the heat, what the weather might be, you know, all those kinds of things which are, you know, ingredients for habitability. So if we can get more data on cooler planets, we have lots of data on hot planets now. You know, between the ground-based data and JWST, lots of data on hot planets. So we're getting better at being able to model atmospheres. But what we want to do is model cool atmospheres more accurately. So we'll be able to get this data, which is pretty exciting. Now, because it's a tech demo, it's only going to do this for, you know, up to maybe 10 systems. But if it all goes well, then they're going to have more time to look at other things. And there are a few other questions that they're interested in, like, you know, how to do this around binary stars instead of single stars, because that'll really help us in the future. And it will be also being able to observe debris disks and extragalactic light, which is like the dust that's left over from a protoplanetary disk, which glows. You can actually see it from Earth. If you're in a dark side on Earth, you can see our zodiacal light, just the dust that this is reflecting a little bit of sunlight. But importantly, all of this is building towards what will be NASA's next big exoplanet direct imaging flagship, the Habitable Worlds Observatory. So that one will be designed to take actual images of Earth-like planets around sun-like stars. So Roman is a really important step on the way there for helping us both model exoplanet atmospheres and get this technology working. Okay. But we're not just working with a coronagraph with the exoplanets. We also have, as Amy said, the Wide Field Survey Imager. So the strength of Roman is that it's a survey instrument. Strength in numbers. It's going to do so much very, very cool stuff. So one of the things it will do is a survey of the middle of our galaxy, the bulge at the center of our galaxy. And it's going to use the microlensing technique to look for planets. So microlensing relies on the fact that everything with mass bends space-time around it. So if you're looking at this star in the center of the galaxy, and between you and this star, another star comes between, that star that's coming in between actually bends the light of the background star around it. Now, you don't necessarily see this star. This is the bright star in the background. What you see is this star get brighter and then fainter again. And if the star that's coming between you and the background star has a planet, you actually see two peaks. The planet and the star both act as little lenses on the light. So that's microlensing. It's a very successful technique. It's found over 100 planets so far. And importantly, it's the sort of thing you can do on many stars at once, which is why it's a good survey strategy. Okay, so we're doing this survey of the galactic bulge. So here's an image of the galaxy that Amy showed earlier. This is the center of the galaxy. This is where the supermassive black hole that you saw the photo of last year is, in the center here. All of these dark lanes are dust. So this is all dust here. So this is one of those fields, one of those, like, you know, Space Invader fields that Amy showed. So the survey is 7 of these fields, 7, so the numbers are a little in flux, but 7 fields, and And each season, so of the 5 years of the mission, each season they'll come back and spend 70 days just staring at this patch over and over and over and over and over again. And they're going to look at 100 million stars. Now, the galaxy's got 100 billion stars, so we're looking at 0.1% of the stellar content of the whole galaxy for planets, which I think is pretty exciting. So how many planets will we find? So we're estimated to find something like 3,000 new planets. Now, currently we have about 5,500 planets, so this is a big increase on what we already know. But the most exciting part is that these planets will be different from the planets we already know. It's not 3,000 of the same, it's 3,000 different planets. So this is a plot showing, as a function of the distance from the star, the planets that we found so far with Kepler in blue, and the planets that we've projected to find with Roman in orange. On the y-axis here is the mass of the planet. So massive planets at the top and small planets at the bottom. Close to the star is over here on the left, far away from the star is over here on the right. So 1 AU is the distance of the Earth from the Sun, and 1 Earth mass is the mass of the Earth. So this blob here is Earth. So this is where Earth would appear on this plot. So you can see with Kepler, we did a really good job of investigating inner solar systems out to where the Earth is. We found thousands of planets there. But we weren't able to find much past that. And actually, our sensitivity really started to drop off right at Earth. Roman, on the other hand, with his microlensing survey, is sensitive to cool planets out here between 1 and 10 AU, which is where we're really excited, and also where we'll be able to take this overlap between Kepler and Roman and really hopefully pin down, finally, this frequency of planets like the Earth. Okay. The downside of microlensing is that it's not like we'll be able to come back with JWST and look at these planets in more detail and learn lots of things about their individual atmospheres. Microlensing events happen once, the intervening star comes between you and the background star, and then they never happen again. That star and its planet keeps going. So individual events aren't as valuable because you can't do much with them. They're valuable in the sense that it's new types of systems that you can explore, and that's great, and we'll find new types of systems. But the actual individual systems, we won't be able to learn much more about than we can get from the microlensing curve. But importantly, the exciting thing is that the superset of the population of events, we're going to see hundreds of thousands of microlensing events, tens of thousands of them will have planets, and a few thousand of them will be able to be resolved and solved and found what the planets are. That population of events will tell us about what's actually happening, like how many planets are there, and how are they distributed around stars, and how are they distributed in mass. This is all super exciting stuff. And importantly, we'll get to this question that I've been thinking about for a long time now, which is how common planets like the Earth are, rocky planets in habitable zones of sun-like stars. Why is that important? I'll stop talking about exoplanets in just a minute, but why that's important is this is a plot from the Decadal Survey, which Amy talked to you about. It's just once every 10 years, all the astronomers get together and say, what's the most exciting thing? This is a plot showing, as a function of the size of a putative theoretical future flagship mission, now called Habitable Worlds Observatory, how many Earth-like planets you could find. And so the Decadal Survey recommended that we study the idea of a 6-meter telescope, which would be expected to yield something like 25 Earth-like planets in the habitable zones of sun-like stars. But the slope here is nearly linear and depends very strongly on how frequent Earth-like planets are. So for the Decadal Survey, they assumed 24% of stars like the Sun have Earth-like planets, which was a number from the literature a few years earlier. But that number is actually wildly uncertain. Conservatively by a factor of 2 or 3, probably more like a factor of 5. And that really dramatically changes how big a telescope you have to build. If the frequency of Earth is 5 times lower, then you need to build a much bigger telescope to get a statistical sample. So Roman and Kepler together being able to give us this frequency of Earths is going to make billion-dollar decisions in the future about how big this telescope has to be, right? So the implications for this number are huge. So to summarize, Roman is going to help Habitable Worlds Observatory in 2 important ways. One is by measuring the frequency of Earth-like planets with the Wide Field Survey Imager. And 2 is by this technology demonstration with the coronagraph, which is the actual type of instrument we'll fly with Habitable Worlds Observatory and start to get us along that road to Earth-like planets. All right, I'll be real quick. Okay, so let's talk about non-exoplanet things in the local universe. The solar system. So I messaged my colleague Vanessa Bailey, who's the coronagraph instrument scientist up at JPL yesterday, and I was like, hey, what's Roman going to do for solar system objects with the coronagraph? And she's like, oh, the coronagraph can't do moving objects. And I was like, that's fair. So the point of the coronagraph is, you're trying to get a very, very stable lock on this point source so that you can cancel out its light and look for things around it. So if that's moving, you've just made your job infinitely harder. So that was an easy answer. Coronagraph's not going to do anything for solar system science. The wide field survey imager, one of the things that people are interested in is that we're going to do these deep fields that you're going to hear about in the next few talks, very deep fields. And the way I'm thinking about it is, it's like when you're on a car trip and you're looking at something way off the future and there's bugs all over the windscreen, right? Like you'll see all of the things way off in the distance, but in the meantime, there's all these bugs on the windscreen. I just drove back from the Bay Area on the weekend, so this visual is in my mind. We're going to look through this cloud of objects in our solar system. We've got the Kuiper Belt, we've got the Oort cloud. So when we do these big deep fields, we're going to see these bugs on the windscreen of the Kuiper Belt objects and the Oort cloud objects. So we'll be able to do serendipitous detections of solar system small bodies, which is pretty cool. And then the other thing I found was a suggestion. Our giant planets have lots of moons, and some of them are irregular in terms of their shape and their orbit, and they've been captured. They've been captured by these giant planets and their gravitational pull from some parent population. So I saw a cool idea that we could use the survey imager to, sit on our giant planets for a while and look for more of these irregular satellites and work out what their parent population is. Okay. And then finally, also in the local universe, stars. So this microlensing survey of the bulge is going to find not just planets. It's going to find binary stars. It's going to find brown dwarfs. It's going to find compact objects. There's lots of really exciting science you can do with all of those. For the brown dwarfs, people are really interested in, so you've got stars get smaller and smaller and smaller and smaller until you get to brown dwarfs, and then you have planets. The brown dwarfs are this really interesting class of object in between. And we'd love to be able to bridge the gap between planets and stars and learn more about brown dwarfs, and specifically nearby cool brown dwarfs that we might be able to study in more detail. Microlensing detections of compact objects, by which I mean neutron stars or black holes, which is what happens to big stars at the end of their lives. They turn into neutron stars or black holes, will help reveal the fates and physics of dead stars, how many and what kinds and what's the population. And then finally, we'll have photometry of 100 million stars. And we'll have a lot of really excellent complementary data from Gaia. So that'll help us probe how star formation changes throughout the galaxy with different initial conditions. Do more metal-rich parts of the galaxies have a different star formation function than other parts? So there's lots of really cool star stuff that can happen too. And I think I need to wrap up. So thank you very much.
Thank you, Jessie. That was great. So we will move on now to Dr. Sangeeta Malhotra.
Hello. Remind me, how do I share?
There should be a little screen.
Sangeeta, yeah, there's a little button near the top that looks like a monitor, circular button.
Feeling left, right, center.
Center.
At the top of the middle next to
Oh, yes,
your,
I got it.
you mute.
Got it. So hopefully people can see this.
Looks good.
Yeah, so I'm Sangeeta Malhotra. I'll be talking about galaxies and galaxy surveys. So let me just start by words of my favorite science communicator. What are galaxies? And also, there are billions and billions of galaxies. I've been wanting to say that for a long time. And because Roman will image galaxies by the billions. So this is great. So a galaxy is sort of, you can think of a galaxy as an ecosystem. It's got gas, it's got stars forming, it's got stars dying and letting off gas, and all of that is enclosed in the sits happily in the gravity of dark matter. If we didn't have that sort of gravity, we'd lose the products of one generation, or wealth of one generation of stars would be lost, and we won't get it in the next generation. So, having this sort of structure, this ecosystem is really important to keep the metals on and make things like us and planets and sheep and whatnot. So, and you've heard, some of you have heard this. We've been imaging, doing deep imaging, see galaxies. We see nearby galaxies. We also see faraway galaxies, different kinds of galaxies, irregular galaxies, spiral galaxies, galaxies which are sort of more elliptical and don't have too much star formation. Now, we see these galaxies both nearby and far away, but the relative numbers change because these galaxies evolve. And Roman will do cosmology, but it's also nice to remember that these galaxies are not just point sources and they evolve. So studying galaxies for their own sake is also fun. So, you've heard about the wide field of Roman. Here's the famous Cosmos field. It was tiled with something like 600 tiles, and this is Anton Kokomo's paper from 2007. That's the left thing, and right. So that is 600 tiles roughly. And on the right, you see one field of view of Roman. So in terms of covering large areas, Roman will be very, very powerful, in case you haven't heard that already. So, but I'm sort of a visual person, so let me just give you a sense of it. Suppose Manhattan was the universe or a galaxy. I mean, there are people who do believe that Manhattan is the universe. And your friend goes to visit Manhattan and you say, hey, please send me pictures, right? What does it look like? The first day you get this picture and you say, is that all? And then second day you get this and you get this and keep getting more and more pictures and you say, wow, Manhattan looks very different from day to day. And then suddenly your friend acquires a wide field camera and sends you this picture. So this is the sort of difference we're talking about. I mean, not just in terms of we'll get more galaxies, but in terms of, yes, we'll get a complete picture. So the relative sort of pixel sizes are sort of portions of image and all. I've scaled them roughly to the sizes of Hubble's WIFC3 and Roman. So that sort of gives you a visual idea of what we'll be going for. So, what is that going to do for us? So, okay, in addition to that, the other thing we're going to be doing is we're going to do three-dimensional mapping because we'll get spectra. So there's a prism and a grism, and they will disperse light not for selected objects or the objects we like or objects that are bright enough, but for all the objects. This is called slitless spectroscopy. So we will get redshifts for everything we can get redshifts for. And as in where we see distinct features, and we estimate something like 20-30% of sources will give us redshift. So not only will we get a two-dimensional view of what the sky looks like in galaxies, we'll get a three-dimensional view. And one of the surveys that did that, last survey that did that in a huge scale was Sloan. So this is, I'm showing a sort of three-dimensional view of, pseudo three-dimensional view of Sloan. On this side, you're seeing the all the way look back time to the Big Bang, 13.7 light years away. And Sloan and these are the things Sloan saw. And you can see that nearby part is up to about 2.5 billion light years away. It's well populated because they got redshifts and then things got faint and only the bright objects got redshifts. And here, as you see in the distance, those are quasars. So not every galaxy, but quasars. So that's also sparsely populated. So that's the from here to so on the right is the thing that shows from here to the Big Bang, and this part on the left is the expansion of that inner circle. And you can see there's a lot of structure there. It's sort of like foam or bubbles or whatever you call it. So there is a good amount of structure that you've seen. And just to put a rough idea of what Roman will be able to do, we'll get redshifts in the blue shaded part. So we'll go from about 6 billion of years down to 11 roughly, and map this in 3 dimensions in as dense a thing as Sloan has done for the inner thing. So I personally am very excited about the 3-dimensional aspect of it. This is very, very unique. Well, Euclid will do it too, but not as. So why do we want to do it? Is it more? Are we being greedy? We want more galaxy, or do we just like to say billions, like Carl Sagan did? And no, it's to get a fair sampling of the universe. You know, this is from simulations from Aaron Young. He'll talk more about this. And we see the structure in the universe. It's on the sort of scales on which Roman will probe, it'll average out so much better than on the scales in which Hubble will probe. So it shows the, you can see the Roman and the Hubble footprints there. And not only that, this sort of foam and structure and clustering that we're seeing, it's gonna change. It changes with time. Yay. Let's see. Okay, this is a movie. So on this one, you'll see this is a light cone that Aaron Young produced in collaborators. So 10.5 billion years ago, the foam looked like this. 12 billion years ago, the foam had not evolved so much. And 13 billion years ago, we are almost to the reionization era. It looks different. So we're also going to see the evolution of what that clustering does. And that's going to give sort of cosmology things. So now I'll just talk about some of my favorite things. These are some of the earliest JWST data, and we're sort of picking out slightly small, somewhat unremarkable things, maybe remarkable. I mean, they're not the most massive galaxies or anything. They're small, they're red, so they're high redshift. But when you look at the spectra, that's when it comes booming to you. What's going on here? So those 3 objects, they're represented by the lower red spectra, those squiggles you see. And what you see is in the spectra is that these emission lines, which is basically gas that's being heated up by very young stars and gas that's glowing, that's what we are seeing. And we can get the temperature of the gas and how polluted the gas is with stellar products of oxygen and things like that. We can get all of that, and it's very, very exciting. Oops. So just to show you a comparison, and this is, when this was being shown in the press release, and we were watching it on TV in our living room, and we said, oh my God, this looks like the green peas we've been studying for so long. These young galaxies that we've been studying at very low redshift. This one is 0.01 redshift, and that's the green thing on top, and red thing is at the bottom. Redshift 8.5. Sorry, let's go back. And they look very similar in terms of the nature of the spectrum, and they also, in the images, they look very compact. So just this connection between, things quite nearby and things at high redshift. So does that mean that nothing has changed? No, that's not it. These low redshift green peas of things are also very young galaxies, like these high redshift ones. At high redshift, there's lots and lots of them. At low redshifts, you have to hunt hard to find them. So, what what will Roman be able to do? Roman will be able to find some 20 million or so of these sort of green peas galaxies. And because it's going to get the spectra, which will show these lines, we'll see them as, interesting things right away. We won't have to sort of squint at the images and say, oh, is this interesting or not? Because they're not, frankly speaking. This is an image only a mother can love, or a scientist who studies them. So covering the time period between the sort of nearby green peas and very young galaxies we're seeing to where JWST is saying we'll get these sort of young emission line galaxies in millions. So I didn't get to say billions. That's okay. Another thing we'd be able to do with large surveys of the sky, we'd be able to say, okay, these crowded regions, they develop faster, over dense regions, the less dense regions, there the galaxies develop slowly, like teenagers in cities are, much more savvy than, anyway, I won't go further. So what will Roman be able to do uniquely? Get environmental effects in galaxies, map nearby galaxies very efficiently. We saw that, Ami showed some of that. This is our neighbor Andromeda. That's one footprint of Roman, and there's a moon to scale. Other things we'll be able to do, find rare objects, high redshift quasars, massive black holes, well, I don't know, some other rare objects we don't know about. And then the main sort of goals of which we are marching through, get the geometry of the universe. How is the geometry or evolution? How is it influenced by dark energy, dark matter? Then we'll have another presentation of what goes bump in the night when we're doing time domain, flickering sources, supernova, black holes devouring stars, other things. And then, of course, I really fervently hope that there'll be new science that we haven't yet dreamt of. So that's my email. If you want to get in touch with me later or something, I'll stop now. And if there are questions, I'll be here. Stop sharing.
Thank you, Sangeeta. That was lovely. Loved the New York City skyline analogy as well. That was fabulous. So I'll now welcome up Dr. Benjamin Rose. He will talk about the dark universe and Roman. Before I make it.
Yeah, that one.
The talk?
Yeah, yeah. No. It's the keynote.
This one?
I'll do it. It might be me.
No, it's Sangeeta. Sangeeta.
Okay, yeah, thank you for inviting me to this. Thank you for everyone who came, both in the room and online. I got asked to tell you about the dark universe. Stealing one of the punchlines, we're trying to figure out what is the 95% of the universe. Okay, so what is the universe? So if we're going to look at the dark universe, what's the universe as a whole? So we've talked a lot about stars and galaxies and planets. We could talk about telescopes or people or the ecology or whatever we want. But all of those sort of standard things that we're used to calling matter, when we actually look at trying to figure out what is the universe and how much is in the universe, Everything we see, and we count it up and add it up, it's only 5% of the universe. That's weird. It only gets weirder. So when we count up the entire universe, we find out that 25% of it fits into this bucket that we've labeled dark matter, and roughly 70% fits into this other bucket called dark energy. They're not related, even though their names are. We'll get into it. So let's start with dark matter. Dark matter is really similar to matter. Great, it has matter in the title. It seems to be some sort of thing, some particle, it seems very physical. But what really separates it from the normal everyday matter that we're used to seeing in physics and talking about in astronomy is that it doesn't interact with light. It doesn't shine. It doesn't care about electricity and magnetism. It's not a proton or an electron, none of that stuff. But what we see is we see it in sort of gravitation. So here's a simulation of some of that cosmic web, some of that foam that Sangeeta was talking about. You can see here how the dark matter, which is simulated as these like blue wisps, are influencing how the observable matter, the stars and the galaxies, those bright objects. So the dark matter is influencing the galaxies and where they go in the universe. And it's all due to the gravitational potential. When you have 25%, when you have 5 times more dark matter, it dominates the gravitational potential of the universe. So it tells normal matter where to go. And we've been looking at the universe in a lot of different ways, and we keep seeing this sort of need for extra matter, need for extra gravity for over about 100 years now. So this non-light interacting gravity has a lot of observational evidence for it, even though I call it a quote thing. And then we can go real weird and go to dark energy, which is just a pressure that pushes space out. What? If that doesn't make sense, that's good, because it doesn't make sense. So if you have the Big Bang, where the universe starts expanding out from this hot sort of explosion, you expect it to start slowing down. All explosions slow down. A ball you throw up, it slows down, you catch it. Well, with dark energy, it ends up pushing and re-accelerating that expansion. So this ball will start slowing down as you throw it out of your hand, and then all of a sudden shoot out like a rocket. Just the energy it just comes from, I don't know, pressure of pushing space. It's strange. But so this dark energy is some pressure we're seeing that's causing the sort of the accelerated expansion of the universe. What really, really makes it weird is we have a lot of theoretical explanations for dark matter. A lot of people are looking for it and trying to understand what it is. We have one good initial idea of what dark energy would be. And when you do the theory about how strong dark energy should be, and you look at how strong it actually is, you're off by 1 followed by over 100 zeros. It's not a factor of 10, it's not a factor of 100, not a million, not a billion, not a trillion. It's 1 followed by 100 zeros off. We really don't know what's happening here. We see it, we see this accelerated expansion, and we have very little idea about what's actually causing this pressure. So yeah, welcome to the crash course in cosmology. Now we're transitioning over to Roman. So the Roman and the dark universe. To understand dark matter and dark energy, we're really going to be using 2 of the 3 main core community surveys: the High Latitude Wide Area Survey and the High Latitude Time Domain Survey. These are both looking outside of our galaxy, outside the plane of our galaxy. One looking at the extremely wide area, over 2,000 square degrees, and one looking at a much smaller area, 10, 20 square degrees, but repeatedly over and over again. So this allows us to measure millions of galaxies and thousands of precise distances. And we'll get into more about that now. So in the Wide Area Survey, we're using a tool, a method called the 3x2 point measurement. Welcome to astrophysics, where we name things in a very weird, convoluted way. So the 3x2 point is 3 ways of comparing 2 things. It gets a little bit more detailed, but that's enough of it right now. So it's the 3x2 ways, by comparing 2 things. So what we compare is we compare the location of a galaxy to the location of all the other galaxies. Or, one of the other ways is the shape of a galaxy to all the other shapes of the galaxies. Or the location of one galaxy to all the shapes around it. Yeah, and so for more technical terms, location is galaxy clustering. Shape comparisons is cosmic shear. What does this actually look like? So, if you start back at the Big Bang, you get the universe is very hot, very much like a soup, like this sort of flow, this liquid state. And what happens is you get some quantum fluctuations in that level. And so as it expands and cools down, those sort of turn into sound waves. And so as it's getting bigger, it's no longer this foam, but it's turning into like any other sort of water or any other sort of fluid, and you'll get sound waves in it. I really want to start this over about here. So here you get the sound waves coming. Oh no. Okay, we're going to start from the beginning. So you get these sound waves sort of propagating out through the medium. And they end up getting frozen in. So here they're propagating out, and here they start to freeze in place as the universe gets to a certain certain temperature. And it's at those sound high density pressure points where you'll get an overdensity of galaxies. So when you're looking at a galaxy's location compared to the other galaxy's locations, you'll start to see this characteristic length scale from those initial sound waves from very early in the universe. We can take questions now or later, I don't care. I know it's complicated. The other main thing from the high latitude wide area survey is looking at galaxy shapes. So in cartoons, galaxies look like this. In less cartoonies, Sangeeta showed you a little bit more of what galaxies look like. But really, they don't quite look like that. Sangeeta's real images are much closer to just points on an image like this. So you'll have this intrinsic sort of shape of these galaxies, but this actually isn't reality, even though we see it as 2 dimensions. The real world is 3-dimensional. So there's a distance here. And so you have the intrinsic shape of the galaxies, but also the light as it propagates from far away to nearby, from this red edge to the blue in this picture. The large-scale structure, the matter between us and that galaxy, tweaks the light a little bit, bends the shapes a little bit. This is all the gravitational lensing that was brought up earlier. And so your measured shapes is a mixture of the intrinsic shape plus modifications to that from the large-scale structure. So as you want to understand the dark universe and how dark matter is influencing the structure of our universe, then you can separate out the intrinsic shapes of galaxies and the large-scale structure imposed shapes on those galaxies. And then that gets really complicated. And ask Ami, because that's what she knows that. She does that. I don't. That's about as much as I can get. But there's a way to separate those out, and you can actually start investigating the shapes from the large-scale structure and learn about the large-scale structure of the universe. What I do is I do supernova cosmology. So this, you can ask me all these questions. But what we are observing here is this is in the time domain field. Because what we're trying to look at is these exploding stars. So we need to observe them before, when there's no explosion, pre-explosion, during the explosion, and afterwards. And so these are a certain type of exploding stars that are really unique because we can get distances from them. And so intrinsically, they are roughly the same brightness, no matter which one you ever observe. That roughly is where I get my pay, to understand that, and to make that more true and less roughly. But that means if you observe a bright 1A, it's close by. And if you observe a faint 1A, it's farther away. Because like any sort of candle, this is where the standard candle comes from, as you walk a candle away from you, it appears fainter. So that's what we use, is we take the brightness and we can figure out how far away it is because we know they are all the same brightness-ish. We're not going to get into the ish. And so that allows us to make this very simple diagram called the Hubble diagram, where we have distance of objects and redshifts. Redshifts were brought up recently, but I'm going to go into a little bit more detail. So because of this space, because the universe is expanding from the Big Bang and the acceleration of dark energy, galaxies that are farther away from us are moving faster away from us. Just there's more space between us and them that is expanding and adding to it. So in this case, the real thing that matters is that it shifts a galaxy's light to become redder. So if the galaxy is originally blue, it'll start looking more red the faster it's moving away. This is the same exact wave mechanics that is the Doppler effect. If you ever hear a siren changing its pitch as it's coming towards you and then goes away from you, that's the same effect that we're seeing here, except for it's not coming towards us ever. It's just redshifting away. So now we have redshifts for all of our objects and distances. So if we dig into Adam Riess's and others' 1998 paper, this was the discovery of the accelerating universe. They really set out in that decade to measure how big the universe was, how big it was, and what was in it. And so what happened is they're very far objects, very far away, here at 42, on whatever scale this is, don't worry. They were further away than expected. These standard candles were fainter than they should have been. Somehow there was more space between us and these distance objects than we were expecting. So if you dig into this bottom plot, it's the same data, just slightly different axes. You can see the data points are all here in black. There's about 50 of them here. And then there's 3 different cosmological models shown here. And so this bottom one is lots of matter, lots of gravity. The Big Bang explodes, and then all sort of collapses down because there's enough gravity to pull it in. That doesn't fit the data. Some matter, some gravity. Sort of the Big Bang explodes out, and it slows down because there's gravity sort of slowing it down, but the explosion had more energy than gravity can do. Sort of fits. But what really fits is a universe with some matter, but also this pressure that's pushing it out and accelerating the expansion. So this was weird because this was one of the first observational evidences of that accelerated expansion, that we were expecting a deacceleration, the explosion sort of slowing down, when in fact we're seeing it speed up. So I was asked, what will Roman do? Because I haven't talked too much about Roman. Roman will increase our knowledge of the parameters of dark matter and dark energy by a factor of 3. So right now, we know how much there are, and we know sort of how clumpy dark matter is, and we know sort of called the equation of state of dark energy. This is how much like a pressure it is. It's weird, complicated fluid dynamics. But these parameters we should get sort of on a baseline average, a factor of 3 improvement of what we have today. So this is the current best published release for a type 1a supernova cosmology analysis. Remember that the original discovery of the accelerating universe was about 50 objects. This is about 1,500. There's another one that I've seen the results of, and they wouldn't let me share them with you, which is coming out later this summer, which will be better. And so we've really improved a lot since the late 90s. But what's a lot of fun is here's a simulated Roman Hubble diagram where we're at 10,000 from Roman. So we're going from 50 to 1,000 to 10,000. And we're really able to get those extra precise measurements of dark energy because it's weird and we don't know what's happening. And at this point, we need more data in order to sort of constrain what it might be. Because right now, there's just too many bad theories, too many theories that don't quite fit the data. And the more constraining power we can give, the more we can point the theorists to where they should be looking. I also like pointing this out. So they liked math units. This is redshift of 1. So here. So you can see there's just a few objects here at redshift 1. I just love that Roman, a large portion of their objects are going to be in this redshift regime at this distance that we've never really probed as well. So for the dark matter and dark energy, Roman's going to change the game, really improve our measurements by a factor of 3. So to quickly summarize, dark matter sort of acts like normal matter, except for it doesn't interact with light. So it's dark matter. See, that name makes sense. Dark energy is just strange. It's this energy that's pushing the universe out, accelerating the expansion. Roman will improve our measurements and our knowledge of both of these, the entire dark universe, making up 95% of the universe. And it will do this through both a time domain survey and a galaxy survey, surveying millions of galaxies and tens of thousands of type 1a supernovae. I think we're having questions at the end?
Yes.
Okay.
Thank you, Ben.
Yep, you're welcome.
Side-eyeing Thomas. So scary. Such a laptop.
That starts it.
Yeah, we have one more online person. All right. Thank you, Ben. We have one more talk, which will be Suvi Gezari, Dr. Suvi Gezari, going over the dynamic universe of Roman. And then we're running a little behind, so we'll do a quick Q&A after Suvi is done.
Great. Well, I'll get started. Hopefully you can hear me. I'm very excited to talk about the exciting discovery capability of the Roman Space Telescope in the dynamic universe. We happen to currently be in a golden age of wide-field optical surveys. So we have several telescopes with wide area CCD cameras that are taking movies of the night sky at pretty high cadences of several days, over thousands of square degrees, and they're discovering all sorts of transient and variable objects. And in particular, the most common type of transient that we discover when we look at the night sky in this dynamic way are supernovae. And we just heard about the thermonuclear type 1a supernovae that we use to map out the expansion of the universe. Well, I'm very excited to say that with Roman, we are going to enter the golden age of wide field near infrared surveys. And this is a whole new parameter space to look at the universe over wide fields of views in the time domain, specifically at infrared wavelengths. And not only is the wavelength sensitivity special about Roman, but really it's the spatial resolution. The fact that we're getting Hubble-like spatial resolution over such wide areas of sky is really going to enable amazing discoveries of the dynamic universe. So as we just heard, one of the core community surveys, there are two dedicated time domain surveys. One is called the High Latitude Time Domain Survey, and that is really designed to do this supernova 1A cosmology that we just heard about, detecting thousands of type 1A supernovae to measure precision cosmology. And then, of course, there's this other dedicated time domain survey called the Galactic Bulge Time Domain Survey that will be staring at the center of our galaxy on very high cadences of 15 minutes. And in this case, one of the core reasons for staring at the bulge of the galaxy is to detect these microlensing events. And in particular, this has been designed to be able to detect thousands of microlensing events from planets around stars. And we heard that this is going to open up a really exciting realm of parameter space of looking at these outer planets and colder planets, as well as an entire population of free-floating planets that may exist. But I hope I'll convince you in the next few minutes that this is just the tip of the iceberg. So while these time domain surveys have been designed to discover type 1a supernovae and microlensing planets, in fact, there's a whole other set of phenomena that the Roman Space Telescope is going to discover in the dynamic universe. And I'm going to be telling you about some of these exciting science cases. So we heard about microlensing by planets around stars. Well, we also will detect isolated compact objects with this Galactic Bulge Time Domain Survey. And in particular, we'll be able to detect long-lived microlensing events that are coming from the microlensing by isolated neutron stars and black holes. And what's really special is that with Roman, not only do you get the light curve of the microlensing event, but you also measure the astrometric deflection, the way that the star is not only magnified by the black hole or neutron star passing in front of it, but it's also deflected in its position on the sky. And so Roman's sensitivity and angular resolution allow you to measure both. And we can even combine Roman imaging with ground-based imaging, for example, from the Vera Rubin Observatory, to measure precisely the masses of free-floating black holes. And this has already been beautifully demonstrated with Hubble follow-up imaging of a microlensing event discovered on the ground. And in fact, the combination of the light curve and the astrometric deflection measured by Hubble enabled the precise measurement of a 7 solar mass free-floating black hole. Roman is also going to be a very powerful observatory for serendipitous discovery of strongly lensed supernovae. So we've already been discovering these strongly lensed supernovae with the Hubble Space Telescope and just recently with the James Webb Space Telescope. And what's really exciting about this phenomena is that if you can determine that you have a multiply lensed supernova 1A due to strong lensing from dark matter in a galaxy cluster, you can actually, if you monitor that lens supernova system and look at the light curves of the individual images of the lens supernova, you can actually measure the time delays of these multiple images and actually get a direct measure of the distance to the supernova, which can then be used to construct a Hubble diagram that's independent of these other methods and could address the so-called Hubble tension that we already see between the parameters derived from supernova 1A measurements and the cosmic microwave background. So we think that just within the Roman High Latitude Survey, there should be 10 or so strongly lensed type 1A supernovae that can then be monitored in time. We also are going to learn a lot about the galaxy environments and stellar populations of transients. So one of the exciting aspects of Roman is because it's going to be covering so many thousands of square degrees with this excellent spatial resolution, is that when we do discover transients with other telescopes, we can look back and precisely pinpoint the location of the transient within its host galaxy and learn about what it looked like before the explosion and perhaps pinpoint exactly which star exploded or what the environment of that transient was. In particular, one area I'm interested in specifically is pinpointing transients in the nuclei of galaxies. And so once again, thanks to the excellent spatial resolution of Roman, as it's surveying the sky, it's going to serendipitously catch transients in its wide area survey. And you'll be able to then determine the exact location of a transient and determine if it's actually associated with the center of a galaxy and therefore likely with the supermassive black hole lurking at the center. And this is going to be very powerful for discovering tidal disruption events, which occur when a star wanders too close to a central black hole and is ripped apart and swallowed by the black hole. And we can use Roman to discover these events not only in nearby galaxies, but out to the very early universe, thanks to its near-infrared sensitivity, which can discover these tidal disruption events at very high redshifts. And in fact, there's an entire phenomena associated with the tidal disruption of stars in which some small fraction of them launch jets. And one of the first discoveries of a jetted tidal disruption event was actually completely missed in the optical because of dust obscuration. And in fact, it was only able to be detected at near infrared wavelengths, although it was discovered in the high energy X-rays. So this will be a wonderful science case for Roman. We also, I hope you have heard, have an entirely new window on the universe, and in particular on neutron stars and black holes, and that is with this ability to detect gravitational waves. And indeed, we have these gravitational wave observatories, LIGO and Virgo, and they're measuring the distortions in space-time due to the merger of neutron stars and black holes in the universe. And from this, we are getting this entirely new window on black holes and neutron stars in binary systems. And we're getting to know the masses that they are before merger and the masses after. And we have a new window on this realm of stellar death. But what's really exciting and why Roman comes into the picture is while these gravitational wave observatories can tell us these two black holes just merged and this was their masses, what they can't tell us is exactly where they were on the sky. And while they do have a localization capability, you still only localize the sources to hundreds of square degrees. So this is where we really need wide field imaging capabilities. And in fact, the first neutron star merger that LIGO and Virgo detected was really fortunate in that it was relatively close by, and it was accompanied by a short gamma ray burst, which gave its own localization on the source of the gamma rays. But in fact, astronomers heroically covered the localization region of that gravitational wave and gamma ray burst localization intersection, and they did indeed detect a counterpart in light in the optical and UV and infrared and eventually radio and X-rays that pinpointed exactly where the neutron star merged and from which galaxy. So this is really an ideal science case for Roman because Roman has both this wide area and near infrared sensitivity and high spatial resolution. And so there are various studies that have shown that we should be very efficient at following up gravitational wave detections with Roman in target of opportunity mode. But also we may serendipitously discover the counterparts of gravitational wave mergers even without detecting the gravitational waves, meaning that we'll detect this near-infrared kilonova counterpart just serendipitously in the high latitude time domain survey. So Roman is really going to be a critical component of this ecosystem of wide field telescope capabilities that are going to be working together to localize what we call multi-messenger sources. These are sources, dynamic sources in the universe that are emitting at various ways in neutrinos, gamma rays, gravitational waves, and of course in the optical and infrared. And finally, with Roman, we're going to be learning about dust-obscured transients that otherwise are missed by optical surveys. But we're also going to be discovering new phenomena that are yet to be discovered. And in particular, I'm excited about detecting transients at very high redshifts where their intrinsic UV optical emission is actually redshifted all the way into the near infrared wavelengths. And so there's a lot to discover, and please stay tuned. Thanks.
Thank you, Suvi. That was great. So now we do have about 7 minutes for Q&A. Thomas, I don't know what's going on here. I'm scared of it. Something is possessing this. I'll switch over here. Oh, I'm hoping this mic is working. There we go. So we don't have any questions online at the moment. So if anybody has any questions in the audience, please raise your hands. Christine can bring our mic around.
Hi, this is a question for Dr. Christiansen. I noticed that one of your slides said, will we see pretty pictures? And that might sound kind of frivolous, but as a science communicator, I think we all want to know, will we see pretty pictures? I know that we'll see movies, but I don't think we'll see things like Hubble and Webb have shown us so far, or am I mistaken?
Right. I did include that on purpose because I think we've come to expect a diet of pretty pictures from Hubble and Webb. So the wide field survey imager will take lovely, big, deep, like wide images, like, you know, Amy showed at the start, the contrast between the Hubble field of view and the Roman field of view. So Roman you will see large fields of view, but you're not going to get the pixel scale is very different. So the resolution, the detail that you can see is not the same between these this is the sacrifice you make. You can look at more sky, but with less detail. So it won't be the same. They'll still be gorgeous things, but they're just not going to be this like incredible detail that like Webb is showing us. And in particular, I put that point there for the coronagraph because, you know, we're directly imaging planets, which makes it sound, you know, very wild and fantastic and exotic, but it's going to be a blob, like a little blob. So that's good for you to know in advance.
Oh, okay, sure.
I have a very, I don't know, maybe not so wise question, but like in microlensing, how you can know if it's like a stellar black hole or a star? Because you basically are not seeing nothing, right? You're seeing just the enhancing in brightness. So I
Suvi,
mean,
do you want to take that one?
Huh?
I was saying, does Suvi want to take that one? She thinks more about microlensing of black holes and stars than I do.
Yeah, so I'm not a microlensing expert, but I think you are correct in that the thing that you measure from the microlensing is the mass of the object. And so, of course, you could have a 3 solar mass star or a 3 solar mass black hole. But I'm pretty sure that I think that you can also, if it were a star doing the microlensing, you would see the star. And so that would contribute to the light. I don't know if am I wrong about that? So these are special in that the object that's doing the microlensing is intrinsically dark.
Yes, no, I think you're right, Suvi. And one of the good things about Roman and the fact that we will come back to these fields again and again over the 5 years is that gives a long enough baseline for the 2 sources of light, the background source of light and whatever the intervening thing is, to separate enough. And we have high enough precision with Roman to actually be able to tell them apart. Just recently, actually, they were able to do this for a microlensing event, and then they showed that the progenitor star of the event must be a white dwarf or something fainter because they didn't see light. So I think you're right, Suvi, that we will be able to determine whether or not it's a star or a black hole by this separation and being able to tell how much light whatever it is emitting.
So we had one more question in the room. I'll revisit 2 questions that we had in the chat, and then we will get to our question in the room. I'm guessing this one should be for Suvi again. Can you shed some more light on how we will observe transients using Roman?
Yes, so we have 2 actual time domain surveys. So we have the high latitude time domain survey, which is, we heard today is going to be around 20 square degrees, cadence of 5 days. It's going to be detecting thousands of supernovae, as well as all sorts of other phenomena. And the way we'll be detecting those transients is by using difference imaging. So every time Roman takes a new beautiful image, we'll subtract off an older image and look for just things that have appeared or disappeared. And then we have this exciting high cadence view of the galactic bulge, which we saw will be those 7 pointings. Will there be looking, I think, every 15 minutes. And there it's a very crowded field. So you have to do very careful difference imaging and photometry to measure the fluxes of all the different stars as well as any background objects. But that will be done very carefully because people want to do microlensing. The thing I'm excited about is also just catching transients in the high latitude survey. This is not the time domain one, but just the wide area survey over 2,000 square degrees. That is going to cover parts of the sky that are going to be monitored using other telescopes. And so you may not catch the transient when it's on, but you'll maybe have an image of the galaxy before it exploded to high detail. But you'll also serendipitously discover some transients in that wide area survey, especially if we look at it a few times. So there are lots of different ways in which we can see transients.
Thank you very much.
And we can point the telescope in a target of opportunity to follow up events.
All right, thank you.
And then I'll visit the one more question we have online. This one's for Dr. Ami Choi. One of your first slides showing the instruments on board Roman indicated a part called the serviceable spacecraft module. With Roman at L2, how will it be serviceable?
There's no plans that I'm aware of currently to actually have any servicing missions out to L2. But there are some accommodations on this spacecraft, which I guess, yeah, maybe there's some future possibility. But yeah, currently, actually, there's nothing planned for that. It's just there are some aspects of the spacecraft bus structure that would potentially allow for some servicing.
Thanks, Ami. Christine, did you want to get our question in the room? Then we have one more online, and then we will release you.
This is a question for you. I must call you Dr. Duke. Anyway, Dr. from Duke.
That's fine.
Am I understanding correctly? You showed a graph that showed, I guess, what the data would look like if the universe were kind of gravity dominated versus balanced versus dark energy dominated. Mm-hmm. So am I understanding correctly that the survey, the supernova survey, are you effectively just like adding points to that graph to understand that line better? Is that kind of what we will do? And how many more points, like how much better will that line get defined?
Yeah, so it is both adding points to the area that we've observed, but we'll also extend it to higher distances than we've ever observed before. And so both of those allow us to not only understand sort of the type of pressure that dark energy is, but what I didn't get into is is currently there's no constraints, no solid constraints on the time dependence of dark energy, because it could change its properties over time. Currently, our understanding of that is very loose, and there's a lot of uncertainty. But with Roman's both large number of points added to that line and extending to higher redshifts, larger distances, we will actually, for the first time, make pretty good, roughly 10% constraints on the possible time dependence of how dark energy interacts.
Thanks, Ben. And then we will visit our last question. I feel like this could go for a few of you, so I'll see who is most excited about taking it. Regarding High Z supernovae 1A and the Hubble flow, some uncertainties have entered that discussion. Will Roman treat them as standard candles?
Yeah.
We can follow up with this. I'm familiar with who asked this, and we can follow up with them.
That sounds like a question for Ben.
Yeah, so High Z and Hubble flow, I'm not quite understanding that, but let's just stick with the High Z for now. That is a question, is when we're probing this new regime, how similar is this stellar explosion when it's happening 10 billion years ago versus now? And so we do a lot of checks. We retrain our standardization models. And so we'll have some objects from Roman with a lot more data. I didn't talk about the spectroscopy, but we'll have really precise measurements at a lot of different energy to complement our wide photometric data with less energy resolution. And so we can, we're planning on testing that. We won't really know until the data's here, but it is definitely a question, is are these objects the same 10 billion years ago as they are now? And that's that is a part of the standard candle-ish that we do and we focus on.
I just want to point out this might be a nice synergy with JWST in the spirit of this conference, that we should be doing some dedicated studies of high redshift type 1A supernovae with JWST, with spectroscopy and detailed light curves, sort of in anticipation of using them as standard candles with Roman.
Thank you. All right, so I will close out our writers' workshop with a big thank you to our speakers. I personally found this super useful. I know a ton of other people will as well, including journalists, writers. So thank you very much, and we close out for the day.